All right, good morning. My name is Ahmad Alhasan from Iowa State University, the Institute for Transportation, associate research scientist there. And today I'll just talk about point clouds in general and LiDAR for pavement condition assessment. So LCMs and all other 3D technologies are growing now. Everyone knows LCMs, or most people do, working with pavement condition assessment. So my presentation is not focused exactly on one specific technology. It's rather about the analysis approach, the process, how to get there, and some parts of the math behind it. So LCMs is one approach. Photogrammetry using UAVs is another approach. And the approach we've used in a couple studies actually is stationary LiDAR. So stationary LiDAR is a little bit slow compared to other systems like LCMs or mobile LiDAR, but the advantage of stationary LiDAR is the very high accuracy of the system, and it has been tested against inertial profilers, and it's giving very exact measures, I would say, with very high accuracy, and sometimes even exceeding the capabilities of inertial profilers, amazingly. So we've used LiDAR in a couple studies for road geometry and RI calculations. We were focused on monitoring over time. So if it's a specialized study, it's not about big system going out every once in a while to scan the entire network. It's rather about one section at project level. We're trying to detect changes over time. So we did scans over gravel roads, we did scans over paved roads, we even did scans for construction to find volumetrics and roughness parameters of the pavement surface. The other part of, actually we have a couple studies on this. This is another study on using photogrammetry as a cheap alternative. In here we're doing basic stuff, we're using cameras, we're not using UAVs, anything. We're trying to focus on the analysis approach. Even in one of the studies, we've used a phone camera, an old phone, and it works. So getting point clouds out of photogrammetry is something possible using very cheap technology if you're trying to capture a few things. In the project site, you have all these sophisticated equipment, and you would like to document the 3D of a small section while people are constructing. You can take a couple pictures and reconstruct that cloud later. So in here, this is the reconstruction process or sifting process. We have all these images captured in the top surrounding the entire section, and then below that, all that scattered point is actually the point cloud created out of the photogrammetry process. So the process goes about stacking these pictures and then matching key points in each picture, and some algorithm would start creating some 3D models out of that. It's not a new technique, photogrammetry itself, but the use of it and the software tools available now in the open source, it's growing, but it's not yet too fast. I mean, to regenerate this point cloud, it took us about 30 hours. So it's nice, but it's still under the process of development. Some of you would go like 30 hours, that's way too much. UAV systems can generate much faster. That's true, but we're trying to capture higher accuracy because photogrammetry, it's good for, I would say, network level, the location of the road and all that. But with this study, we're trying to assess roughness down to hopefully macro texture. We couldn't get there, but it's in the process. Some other people got there. So this is a video showing the stacking process and generating the point cloud. The tough part that takes time is not generating this initial cloud, because initially you create a sparse cloud, and that's what most UAV systems do. They create sparse clouds. Sparse clouds can be created really fast, within a couple minutes. But if you want to get very dense cloud, you have to wait for a long while. Now, the other part I'd like to talk about is also matching the clouds for visualization and analysis. So matching clouds over time is very crucial. In many cases, projects, people go out, collect clouds, it's nice, beautiful, But if you want to do some comparison over time, you start running with problems that you don't have your clouds matched if you don't have proper coordination. GPS system, yes, you can match, definitely, but if you're going down to very high accuracy, you're trying to capture some kind of roughness analysis, IRI, texture, stuff like that, you would need more or higher accuracy in matching clouds. So the way we went around it was setting targets in the field, monuments to some extent, and leave it there, come over time and scan and try to match the clouds in post-processing using these targets. We've captured pavement during construction. This is a melt section, and we're trying to capture before and after. And with the 3D point cloud, we could visualize the changes in volume and how much asphalt was applied or concrete was poured. Now, stationary LiDAR is not the optimal, I would say, technology for this. However, it has one big advantage for PCC sections. If you want to acquire scans during construction, especially with the new generation of laser scanners or LiDAR, the solid state LiDAR, you can acquire more and more point clouds in actually I'd say matter of minutes, and you can acquire that on the side of the road, and so you can capture the surface properties, especially with the advantage of LiDAR being some extent highly accurate. Now, part of the study was comparing, or one of the studies was comparing SFM and LiDAR. SFM is sifting or structure from motion. We're trying to get point clouds using, again, I've talked about that, the photogrammetry and LiDAR. LiDAR works very well, but if it's fresh asphalt, you won't get points. You'll get just a few of them, and then asphalt would absorb the rest of the point cloud. So we'll get pretty bad point cloud. The one on the left, the gray part is no points at all. So in here, photogrammetry comes in advantage if you have a way to get to the higher accuracy, photogrammetry could deal with it easily. However, on the other hand, if you have very wide, clean surface, like PCC section that has been paved recently, you won't get a nice cloud from photogrammetry. Then you move to LiDAR. So each technology has some disadvantages and advantages that we have to keep in mind, that whenever you're trying to capture data during construction, especially for high resolution. Again, I'm focusing on that because this study was about high resolution. There are tons of applications for network level and geometry. This study was focusing on the surface itself. We're not trying to detect cracks with it or anything, but we're trying to detect rutting and roughness geometry out of that. Now, visualizing the errors itself is also advantageous. So if you have point clouds, 2 point clouds, and you would like to see how they work, it would be really great to create a third point cloud of errors instead of just geometry. So in here, this is a point cloud of errors, actually, not actual geometry. So you can see the locations where you have errors focused, and that would help you analyze the patterns in your errors in your measurements. So if you look at the section, most of the errors are focused or clustered along wheel paths. So that means that helps you to identify the locations where you want to revisit or reanalyze or focus more on, or even suggest new developments. And the reasons for high errors at wheel paths is normally the geometry changes there quite a bit. And if you have photogrammetry technology, you cannot capture all these small changes. You can capture a global change and you can fit something through it. So at wheel paths, you have small changes that you cannot capture, but over the other parts of the sections, you'll have errors going up and down and canceling each other. But at the wheel path, you will have the highest errors, and it's reasonable to conclude that at wheel paths, more investigations are needed if SFM is used. Now, the other aspect, like in terms of visualization for this presentation, don't rely on final numbers always. Try to visualize whatever you have. So these are two profiles captured from SFM and LiDAR. If you do cross-correlation, which is the standard method in ASTM for profiles matching, you'll get 0.99. But they don't look alike at all. And if you analyze roughness on that, you'll get bad numbers. So visualizing the point cloud itself, even in a very simple way, like taking a section out of it, you'll realize that there is some problem in the mathematical process. Cross-correlation relies on, to some extent, the variance of each point cloud. So if you have a very high variance point cloud, which is scattered point cloud, and a very concentrated point cloud, even if they don't match, one of them would eat the other. So the scatter of that first point cloud would eat up all the errors, and it would show up as if it's high cross-correlation. Why? Because the other profile is within that error cloud, I would say, or scattered cloud. So as long as it falls inside it, the cross-correlation won't reflect anything. So if we're comparing two profiles, two profiling techniques, visualizing the profiles themselves is crucial because sometimes numbers can be very deceiving, I would say. That's also another example. It's not out of this study, but regarding the problem on relying on numbers or following simple approaches for visualization as well. So these are two histograms. The one on the right, you can conclude it's binomial. The other one is normal distribution to some extent, or I would say Gaussian distribution. However, both of them are for the same data set, but changing the bandwidth and all that can change your results. And the reason I took this because when you analyze point clouds, in many cases you will end up with bandwidths. So after acquiring our point clouds, we did some roughness analysis, roughness maps. So these maps are created by simulating quarter-car model along a grid. And the grid is predefined on a spatial domain. And out of that grid, we place the LiDAR points, the best match on the center of the grid, because point clouds eventually are randomly distributed on the spatial domain. It's not a uniform grid. So when using such technology, you'll have the point cloud scattered all over the place, even if it's dense accurate, but it's scattered. So you have to come up with a uniform grid to do further analysis in most cases, because most analysis algorithms rely on uniform steps eventually. Something like Fourier analysis even depends on that. The basic math can be generalized. However, if you want to do a software or an algorithm, you have to follow a uniform grid. So uniform grids, the choice of the grid size, the distribution of the grid would impact your final results. So there is a need to tune the grid size and the way that you grid your LiDAR data to come up with realistic outputs. This is also about the concept of numbers and how important it is to visualize your data. Again, this is not for point clouds, obviously, but this is a nice visual tool explaining Fourier transform. Why did I throw this in there? Because when you do roughness analysis, you're basically doing some kind of Fourier analysis. So visualizing your process itself, how the equations work, would really impact your understanding. Because if you know how to visualize it, that means you really understand it well, and that's a step towards automation. So eventually, all that visualization, if you know how to visualize it really well, how to control it, and how to understand what's going on behind the math, that really reflects our capability to move towards automation, because in most cases, visualization tools are just nice pictures, but there's something lying behind them. Understanding that part would also help you understand the next steps. So that's more like a automation architecture for all devices in general. It's a very general architecture. And the part visualization comes in as machine awareness layer normally. So Acquiring the data, looking at the data, that's all machine control maybe or machine behavior, but machine awareness layer relies on visualization. If you can visualize it for your own self, that means you can feed it to a machine and you can feed it to an algorithm. Because if you open a point cloud, for example, in the raw files, you'll find numbers. How can you tell the machine what numbers falls into what grid, how it acts, how it interacts with other grids? That's, in my view, is a visualization problem. If you can visualize it properly and you know how to split these numbers in the right way, then you can feed it to an algorithm, automated algorithm. So eventually, that would help in construction automation. This is an example for intelligent compaction. So if you can, again, visualize it, you can identify the locations of problems. You can set boundaries where you have to fix things for pavement surfaces, and eventually can lead to a fully automated system, which is I'd say the target for automation in construction for pavements, basically. So better visualization means better understanding, and eventually means that we can do something about automation. But at this point, if we don't really understand how to play and manipulate with the numbers, we just show them on the screen, we still have a gap between automation and the technology for data acquisition systems. Any questions?
No question?
All right. Yeah.
I just had a question on the road that you showed there in the picture. It seems like it wasn't paved.
Yes.
That's
were-
not the-
yeah, we're
you
trying-
wanted to pave the road as well?
Yeah, we've applied that to gravel roads, paved roads, construction sites. So we're trying to capture any road surface. And we're trying to understand the mechanism of different surfaces and how they change over time. So gravel roads change rapidly. So we're trying to acquire data on gravel roads so we can see the mechanism and how it changes over time in terms of texture, even down, it's definitely not texture in the traditional sense, but I mean down to very detailed levels.
Thank you.
All right, thank you.